Well, here we go again, and we are in the middle of discussing periodic trends. So let us do a quick review. Last time we were talking about, okay, trends. Let's put down trends here. We were talking about trends in what? Atomic size, right? And when we're talking about atomic size, we're really talking about the radius from the nucleus to the edge of the electron cloud. And we said, hey, there's a trend in atomic size that if I go from left to right, in a period, what happens? My atomic size, my atomic radius decreases. Now, why is that? Why? Because I have a stronger nuclear charge, right? Stronger nuclear charge. Good. Now, we also had a trend going down the periodic table. So in a group, as I go down a group, what happens to my atomic size? My atomic size or my atomic radius increases. And what's the primary reason for that? Well, the cause is that I am adding shells. I'm adding electron shells, and so my size gets bigger. Now, we also talked about the difference between a cation, a positive charged atom, and the neutral atom. And we always said the cation is always smaller than the neutral atom. And why is that? Because it has fewer electrons. Good. This has fewer electrons. And then we also compared the neutral atom to the anion, which means it has more electrons. And why is the anion always larger? This is always larger because it has more electrons than the neutral atom. So that's kind of our summary of atomic size. Let's go on to the next concept. Consider the neutral sodium and argon atoms, which has a larger ionization energy. Okay, new concept here. Ionization energy. So we have a new trend. We want to come down here. We want to talk about ionization energy. And what is ionization energy? Yeah, we always want to start with our definition. What is ionization energy? Ionization energy is, I'm going to need more space. Ionization energy is the energy required, it's the energy required, required to remove an electron from a gaseous atom. Okay, and if we're talking about the first ionization energy, that would mean from a gaseous neutral atom, but we can have other ionization energies. We want to focus on the first ionization energy. Good. Now, so this is my definition, and I think really the best way to understand the trend here is to go back to our wonderful Coulomb's law. Remember, I said yesterday, our last video, that the force between a positive nucleus and the negative electron is equal to K Q1 Q2 over R squared. And we said that Q2 could be thought of as the electron charge, and that's not changing, but my Q1 could be thought of as my nuclear charge. That's my nuclear charge. In fact, we might want to consider it my effective nuclear charge, and that my R here would be the distance between my nuke and the electron that we're talking about. Good. Now, why is this important to us? Well, remember, we're talking about how easily one can remove an electron. Well, what's holding the electron in place in the first place? Well, this force of attraction is what's holding the electron in its space, essentially. So, the greater this force, the harder it is for me to remove the electron, so the higher my ionization energy. So let's think about what two things can affect this force. Well, first of all, nuclear charge. If my nuclear charge increases, Then what happens to the force? Well, this is up in the numerator, so my force of attraction increases. If my force of attraction increases, is it easier or harder to remove the electron? Well, if the force of attraction is greater, that means that nucleus is holding on to that electron tighter, which means that it's harder to remove, which means my ionization energy increases. Good. What about my distance? What effect does that have? Well, my distance, and this could be thought of, the distance between my nuke and the electron. What's another way to think about that? Hey, buddy, look at this. Atomic size. Really, we're thinking about our atomic size, because as my atomic size gets smaller, that means the distance between my nucleus and electron gets smaller. So if my distance increases, if I get a bigger atom, what happens to my force? Well, R here is in the denominator, and it's squared. If it's in the denominator, when it gets big, what happens to my force? My force of attraction goes down, and if my force of attraction goes down, it becomes easier to remove the electron, which means my ionization energy will go down. Okay, so this is the intellectual basis for the trends that I'm going to tell you about right now. Let's take a look at our periodic table, and let's talk about the trends. Let's clean this up a bit. Magic. Woo! I love that, don't you? Good. Oh, man, I left some. Boy, there we go. Abracadabra. Let's think about going from sodium to argon, right? That was the question. I'm going from left to right in the periodic table, right? Now, what happens? First of all, what happens to my nuclear charge? My nuclear charge is going from 11 to 18, so my nuclear charge increases. And so what does that do? We said, hey, if my nuclear charge increases, let's go back, force is equal to KQ1 Q2 over R squared, and that will be my nuclear charge, and here is my distance between them. So if my Q1 goes up, if my nuclear charge goes up, what happens to my force? It increases. Now, we also said, what else plays an impact? Size. Yesterday, our last lecture, we learned that as we go from left to right, my size decreases, which means argon is smaller than sodium, which means my R is smaller here, right? The distance between my nucleus and my electron is smaller, which means my R goes down. R is in the denominator. When it gets smaller, that means my force of attraction gets greater. So what's the overall trend? As I go from left to right in the periodic table, my ionization energy decreases. Woohoo! Got it. Wow. Okay. So what happens? Which one's larger? Well, we said as we go from left to right, it decreases. So that means sodium is larger. Why? It has a smaller nuclear charge, smaller effective nuclear charge, we'll learn later, and it is also a bigger atom, bigger atomic size, which means that what? The distance between the nuke and the electron is greater. Both of those result in a larger, no, that's completely wrong. Which one has a larger ionization energy? It's argon has the larger ionization energy, right? Argon is larger. And why is it larger? Well, like we said, as we go from left to right, it has a greater nuclear charge, which means it's going to hold on to that electron stronger, and it is has a smaller atomic size. Sorry about the confusion there. And both of these lead to a greater force, and a greater force of attraction means it has a larger ionization energy. Woo! Glad I caught that. Man, that could have been a bad thing. Moving on. Consider the neutral sodium and cesium atoms, which has the larger ionization energy. Okay, so where are sodium and cesium? Well, here's sodium. Where's cesium? Okay, now where are we? We're not in the same period now. We're in the same group. Okay, we're in the same group, so that means we need to add another trend here. Okay, so let's add some trends. Trends. Let's go ahead and codify this here. What are my trends? First of all, across a period. What did we say as we go across a period? From left to right in a period, my ionization energy increases. Now we're going to go down a group. As I go down a group, let's take a look at this. As I go down a group, what happens? Well, as I go down a group, my Q1 does what? My Q1 is increasing, isn't it? Yeah, it is. My Q1 increases. So that would indicate that my force may go up, right? But what else is happening? As I go down, I'm adding shells, right? And if I add shells, that means my atom gets bigger. So this guy is bigger. And that means what for my R? That means my R is bigger in my Coulomb's law. So this thing gets bigger. Well, notice, which of these do you think is going to have a bigger impact? My R is squared, and my Q1 is not. And so really, the net effect is, even though Q1 gets greater, my distance has a greater impact, and my force actually of attraction between my nucleus and my electron actually decreases. If my force decreases, what does that mean for my ionization energy? As I go down a group, my ionization energy decreases. It becomes easier and easier to remove an electron. Okay, good. So let's write this in here. What's my trend? When I go down a group, my ionization energy decreases. Okay, oops, we maybe should have said why. Let's say why here. Why, as I go from left to right, does my ionization increase? Because my nuclear charge, my effective nuclear charge increases, and my atomic size decreases. Good. Why does my ionization energy decrease as I go down a group? Because my size increases. And we can add one other thing. The amount of shielding increases. Okay, both of those make it easier to remove an electron. Remember, what is shielding? Well, that's when I have my nucleus, and then I have some electrons that are in the core, you might say, and I have an outer electron, and this electron feels attracted here, but it is repelled by these two other electrons, and this repulsion by the inner electrons is called shielding, right? That is making it easier to remove this because they're pushing them away, say, get out of here. There's too many of you hot electrons by this nucleus. Okay? Good. So let's answer our question. What is the trend here? Cesium or sodium, which has the larger ionization energy? The answer here is, hey, sodium. And why is that? Because it has a smaller size and less shielding. So those two together make it harder to remove an electron. Got it? All right, let's see if you really do. So you guys take a look at this one. Pause me. When you have an answer, come back. Okay, let's find gallium, germanium, cadmium, and indium. Okay, let's find that right here. Okay, gallium, germanium, indium, and cadmium. Let's start up here in this period. I'm going from left to right here. What happens? Ionization energy does what as I go from left to right? Increase. So that means germanium is going to be greater than gallium. Now, and we can also know that what? That also means that indium is going to be greater than cadmium. Now the only question is, what's the relationship between indium and gallium? Well, I'm going down the group here, and we said as we go down the group, ionization energy decreases, which means that indium is less than gallium, and so this is our trend. Cadmium is less than indium, indium less than gallium, gallium less than germanium, right? So cadmium less than indium, indium less than gallium, gallium less than germanium. And why is that? This guy has the greatest nuclear charge, effective nuclear charge, and the smallest atomic size, and that's why it would have the highest ionization energy. That's why it's the hardest to remove an electron from of those four. Moving on. Consider sodium and chlorine, which has the most negative, in a new concept here, electron affinity. Okay, folks, let us get some notes on electron affinity. All right, we have another trend up here, electron affinity, and I'm going to have to take it way down here. I'm going to need more space, don't I? So let's just keep going. Electron affinity. So electron affinity. Affinity. Okay, where do we need to start? We need to start with a definition, don't we? Sure do. We always need those definitions to help us understand what we're dealing with. So what's my definition of an electron affinity? Okay, here we go. It is the energy released. Energy released, okay, when an atom gains an electron. You know, in one sense, this is kind of what? The opposite of ionization energy, right? In ionization energy, we said, hey, it's the energy that is needed to remove. And down here, we said, this is the energy released or the energy given off when an atom gains an electron. So that is my electron affinity. And what is my trend? Well, here's my trend. The trend is that as I go from left to right in the periodic table, electron affinity becomes more negative. Okay, it becomes more negative. Now here's what we have to understand, that from a thermodynamic standpoint, when something, oops, not there, when something releases energy, that's a negative value. Loss of energy is a negative value, okay? So as I go from left to right in a period, my electron affinity becomes more negative. That means what? More energy is lost as we go from left to right. And just kind of a nice little highlight, the halogens have the most negative values. The most negative values. That means what? They lose the most energy when gaining an electron. Okay, and one other thought here is this excludes noble gases. Noble gases are not included in our trend for electron affinity. Okay, so let's go back and see if we have enough to answer the question, enough information. Which has the most negative electron affinity? Here's sodium, here's chlorine. Let's check our periodic table. Where are these guys? Where's sodium? Sodium is over here. Where's chlorine? Chlorine is here. Hey, this is what? These are my halogens. What do we know about halogens? They have the most negative values. Good. So this is pretty easy. Which has the most negative value? My halogen, chlorine. Good. All right. Let's see if you guys can handle this one. Pause me and bring me back when you have an answer. Okay, let's go to our periodic table. We're going to find calcium and bromine. Where's calcium? Here's calcium. Where's bromine? Bromine's here, right under chlorine. Aha, if it's right under chlorine, according to the periodic law, it should have similar properties. So if chlorine is a big negative, this is a big neg, that would mean that bromine is a big neg. Okay? So a big negative there and a big negative, and calcium is way over there to the left, and so it does not have a very large negative value, and so my answer is going to be what? Bromine has the most negative. Does this mean that it gains or loses? Remember, a negative value means that it gain or loss. Does bromine gain or loss energy? How about lose? Does bromine gain or lose energy when it accepts an electron? It loses energy, and it loses a lot of energy. Okay, last two slides, and then we're done. Here we go. The last concept, francium and fluorine, which has the highest electronegativity. Oh man, another new word, and another thing with electro in it. There's all kinds of electros, isn't there? All right, let's go with, we need a new color so you can follow my crazy lines. Here we go. We're going to go down this side. We're going to go with the green. This is our last trend. The last trend, and it's the green trend. Here we go. Green, 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 green. Green, here we go. And the last one is what? Electronegativity. Great, electronegativity. Juliet, are you still awake out there? Good, you better be. Okay, electronegativity. What is my definition of electronegativity? Well, it is what? It is the ability of an atom, and here's something that we haven't really talked about yet, in a compound. So we're not talking about just a naked atom out there. We're talking about an atom that is bonded to something else. It is the ability of an atom in a compound to attract electrons. Okay? So the ability of an atom in a compound to attract electrons. And we'll get into that more when we talk about bonding. And what is my trend? Hey, the trend is simple. Francium is the lowest, and fluorine is the highest, and that's all there is to it. So let's take a look at my periodic table to clarify this better. It'll make more sense with the picture. Here's francium, it's the lowest. Here's fluorine, it's the highest. Once again, we ignore my noble gases, and the trend is this way. So, rule of thumb, the closer to fluorine, the higher the electronegativity, En, the electronegativity. So if you're way over here by francium, it's low. If you're up here, it's high. Got it? Let's answer our question. Which has the highest electronegativity? Ha ha! You know that? It's fluorine. Fluorine wants those electrons more than anybody when it's in a bond. Good. Last question. Pause me, and when you have an answer, bring me back to live. Ooh, spooky. All right, carbon and oxygen. Carbon and oxygen. Let's find carbon and oxygen on here. Carbon is here. Oxygen is here, and the question is what? Which is closer to fluorine? Well, oxygen's closer, so it has a higher electronegativity. Yoink, oxygen. And that would be the end of today. Bye-bye. Hi-ho.